Okay, so we're going to continue looking at probability and continue working with it. We're going to look at a new type today. But before we get into the actual meat of this, let's try and solve this problem. We know the student plays badminton. We know that that's true. So that means the student has to be in this circle. What's the probability that they don't do archery? Okay, well, where do the students who don't do archery reside? Well, these 16 do play archery. They do shoot archery. These 14 do not. So this probability, intuitively, we should be able to reason out that it's 14 over 30, which could be reduced down. So let's look for a second at where this comes from, using more of a probability notation. What's the probability of B? Well, the probability of B is going to be 30 out of 100. There are 100 people total if you add up all those numbers. And what's the probability of A? The probability of A is going to be 38 out of 100. And the probability of A intersect B would be 16 out of 100. And lastly, what is the probability of not A intersect B? Well, that probability is going to be 14 out of 100. So how do we take these things that we just wrote probabilities down for and get this guy here? Well, if you notice, if you look at these carefully, what we've done is we've taken the probability of A not intersect B, and we've divided that by the probability of B. And in general, when we have one of these known statements, the way we calculate it is going to look something like this: an intersection on top and a restrictive amount on the bottom. What we're doing is we're restricting this problem to only those students who play badminton. The rest don't matter. So let's formalize this a little bit. What we're talking about here is conditional probability. What is the probability of A given B? For two events, A and B, the probability of A occurring given that we know B has occurred can be found using this formula. Probability of A intersect B, A and B, divided by the probability of B, divided by the condition that we were given. And if we rearrange the formula, we get the probability of A and B occurring together is equal to the probability of A given B times the probability of B. This is the multiplicative probability law. It says if we want to find the probability of two things happening together, we multiply the first and the second given that we know the first already occurred. And we'll look at an example. So Shu Yi rolls a fair die. Let A be the event, obtain a score of at least 4, and B be the event, obtain an even score. We want to find the probability of A and the probability of B. So the probability of A, well, A is at least 4, so that would be 4, 5, or 6. That's 3 events out of a possible 6. And what we're looking at there is the number of events in the set 4, 5, 6 divided by the number of events in the set 1, 2, 3, 4, 5, 6. What's the probability of B? Well, B is the event obtain an even score, so this is also 3 out of 6. And here we're talking about the number of things in the set 2, 4, 6 with the same denominator as right there. Now we're going to draw a tree diagram for this, and we're going to use this tree diagram to show that the probability of A and B both occurring is equal to the probability of A given that B already occurred, times the probability of B. So on my tree, we know that B is already going to have occurred, so we're going to put the event B as our first event on the tree. So the probability of B happening is 1/2. The probability of not B happening, that is rolling an odd, would also be 1/2. Now we know that A, we're talking about A given that B occurred, not just plain A. So we know that this happened. So we pick 2, 4, 6. So event A is now 2/3 because 2 out of these 3 match the criteria of at least 4. The probability of not A would be 1/3 here because there's 1 out of 3 events that are not greater than 4, the 2. So use this to show that A and B occurring together. Probability of A given B, so A given B would be 2/3 times 1/2, and that equals 1/3 as our final probability. So what is the probability that something is both at least 4 and even? Well, that's going to be 2 out of 6, which reduces to 1/3. So going at it from a conventional approach, we're talking greater than or equal to 4 and even 2 out of a total 6 things. So a 4 or a 6 would be a success out of the 6 things in the sample space. So 1/3, we get the same thing either way. So of 53 staff at school, 36 drink tea, 18 drink coffee, and 10 drink neither tea nor coffee. I don't know how they get through the day, but somehow they do it without caffeine. So what we're going to do to answer this question, how many staff drink both tea and coffee, we're going to arrange our thoughts with a Venn diagram. We have tea and coffee, we have our universal set. Part A, we're looking for this, x. We don't know that. Well, if that part's x, that means that this part would be 36 minus x. And this part here would be 18 minus x. And we also know that 10 people don't fit into either group whatsoever. So what do these 4 pieces have to add up to? Well, these 4 pieces have to add up to our total population. One way to think of this x, using probability notation, would be the number of t intersect c. Whenever you're working with these problems, try to envision or figure out the probability notation for the different regions or probabilities that you're looking for. So, writing this down, we have 36 minus x plus 18 minus x plus 10 equals 53. And solving this, we end up with x equals 11. So now one member is chosen at random. Find the probability that this teacher drinks tea but not coffee. That would be in this part here. So what we're looking for is we're looking for the probability of T intersect not C. We want them in the T circle, not in the C circle. Well, how many people fit the bill there? There's 36 minus 11, or 25, out of our 53 total. Part C, the teacher is a tea drinker, so we know that. Who also drinks coffee? Let's translate this statement. We want the probability that they drink coffee given that we know they drink tea. So, using our conditional probability formula, we have probability of coffee intersect tea divided by the probability of our condition. What's the probability of this intersection? Well, that intersection, there are 11 things out of 53, over probability of t, that's the entire circle, 36 out of 53. This probability is 11 out of 36. Now for part D, I'm going to take a slightly more intuitive approach, and you're welcome to do this on your exams. The teacher is a tea drinker who does not drink coffee. So the probability of not coffee given that they like tea, which means we know that they have to be in this circle, and we don't really care about anything else. So now our possible outcomes is whittled down to 36. And from that 36, we want the ones that don't drink coffee, and that would be the people out here. These people do drink coffee, but the ones that don't drink coffee would be our 25 that do not reside in the intersection. So there is our probability that given we know they drink tea, they don't drink coffee. So that's the overview of conditional probability. You can take a more intuitive approach with it here, but I would always urge you to understand the probability notations and the way that we utilize these formulas that we're given.